All right, class. This is for General College Chemistry 2. It's the first chapter we're going to cover in the course. It's on physical properties of solutions. We have to know more about solutions before we get into kinetics and equilibrium. And it's not a difficult chapter, but I believe students struggle with this chapter because of prior knowledge. So you have to bring with you into this course some things you should have learned in General College Chemistry 1. Specifically, you need to know names, you need to know solubility rules, you need to know um, molecular geometry and polarity, and you need to know intermolecular forces. So all of those should have been covered in Chem 170. If not, you're going to have to go back into the book, and I also have videos on naming and so forth, and watch those in order to successfully navigate um, chapter 13. So the first thing in chapter 13 is these are the sections, and these sections, if you'll change those to questions, then you'll know exactly what you're supposed to get out of each section. So what are the types of solutions? What is the solution process? What are concentration units there? We're going to use quite a bit of mathematics to describe concentration. Factors that affect solubility, colligative properties. Not so much on calculations using colligative properties. We'll skip that or have very little in that. And then we'll talk about colloids, because colloids are important in biology. So before we get started, I think it's important that we talk about what is it that you need to know prior to the class in order to be successful. So let's write down some of those things. So first of all, naming. So let's write that down. Naming. You have to know the names of the compounds that we're going to be working with. If you don't remember how to name, or maybe your teacher didn't stress naming enough, I do have a video on my Professor Chemistry channel, and there's a link to that in the syllabus, and there's also a link to that in Blackboard Ultra. So look at that, look for the video on naming, and I think if you do that, that'll help quite a bit. There's one also on naming acids and bases, so you may want to watch that one too. The next thing that you have to know is Lewis structures. All right, so that was from Chem 170. I'm sure everybody had Lewis structures. And then from Lewis structures, we came up with molecular geometries. And that, a lot of students struggle with molecular geometries. There's a lot of memorization there as to what the geometry is. But in order to know what the polarity of the molecule is, you must know the molecular geometry, because polarity is determined by is there a dipole moment? Is there electronegativity difference between the atoms? And then what is the arrangement of those atoms that make the geometry? So this is pretty complex, and I know my students, they kind of struggled with this, but I think where they struggled even more was the last part that we covered was intermolecular forces. So intermolecular forces come about by knowing dipole moments, molecular geometries, polarity, and then determine what type of intermolecular force is occurring between one molecule and another molecule. Now, in your book on page 565 in table, well, it's at the bottom of the page, they try to do a review of intermolecular forces. They talk about dipole-dipole, hydrogen bonding, London dispersion, and ion-dipole forces. So you may want to look at those things, and you say, why do I need to know this? Well, let's give you an example. So In this class, or we're going to be talking about solutions. And so when we talk about solutions, let me just erase the whole thing there if I can. Let's do let's see if this works. It's not really helping me much. Let's try that. Does that work better? Not really. All right, so we'll have to work on this because it's been a while since I've used this particular pad, and it's not my favorite pad, but it's the one that's working. So let me see if I can. All right, sorry about that. All right, so so here's where we're going with this. Okay, so solutions, mostly what we're going to be talking about in this class is aqueous solutions. So we're dealing with H2O, and you know that is water. You know the Lewis structure for this looks like so. And again, if any of this you don't know, you've got to go back and review it. Otherwise, this chapter is not going to make much sense to you. From this, we know that the electronegativity of hydrogen is 2.1 and oxygen is 3.5. And I have my class memorize that, but you may need to look those up. So that's a difference of 1.4. And that tells you that this bond is a polar covalent bond, that it's unequal sharing of the electrons, that the electrons are pulled to the more electronegative oxygen at 3.5. So hopefully you remember some of that. If not, again, you have to review. That's what we got out of chapter 8 and part of 9. And then, well, the other part of 9 is that we get the molecular geometry. So for this one, we call this AX2 E2, maybe your professor called it AB2, E2. Means the same thing. It means there's 4 things coming off the central atom, oxygen being the central atom. There are 2 bonding pairs, one here and one here, so that's the X2 or B2. And there's 2 non-bonding pairs, which is the E2. So 4 things coming off. The framework for the geometry is that the hydrogen or the oxygen goes in the center, and then the hydrogens are placed like so, and then there's a lone pair coming out at you like so, and there's a lone pair going back through the board like so. So this geometry is the electron domain geometry, and I don't know what they might have called it, the framework geometry or something like that, but the electron domain geometry is tetrahedral, which means 4-sided, and so this has 4 sides to it. There's one side right there. There's another side right there. There's one behind, and there's one below. And then the molecular geometry is what you see. The molecular geometry is what you see with the bonding pairs, which is this one and this one. And so we said water is bent or angular, and if I straighten this up or clean it up, it kind of looks like this. And this is partially negative because it's more electronegative. The electrons are being pulled towards the oxygen. And that creates an overall dipole moment in this direction. That's what that's called, a dipole moment. And because there's a positive and negative end to the molecule, we say the molecule is polar. So water is a polar molecule. So that's going to have big implications in chapter 13, in that we're going to talk about mixing water with other things, or gasoline, or other non-polar substances. Like if you look at methane, it's also tetrahedral structure, and it has 4 hydrogens coming off of it. Again, tetrahedral, just like the electron domain geometries are the same for water and methane, but methane has also a molecular geometry of tetrahedral because there's no lone pairs like there was here and here on the oxygen. So the other thing we know is that the difference in electronegativity between hydrogen and oxygen is zero point 0.4. Well, that's a non-polar bond, which you just called a pure covalent bond or a non-polar bond. So this molecule doesn't have a dipole moment, an overall dipole moment. It's a non-polar molecule. So methane will not dissolve in water because water is polar and methane is non-polar overall. So you go, why do I need to know this? Well, let me give you a real world application. So methane's called swamp gas, and it's made by the decomposition of plant materials or animal materials. And in the swamps, you'll see on the surface, and you can look this up on YouTube. There'll be something bubbling up on the surface from bubbles beneath the surface, and those bubbles can be methane gas, and you can actually ignite them, and you can actually have a flame up here. But because the methane gas doesn't dissolve into the water, it bubbles up through the water and comes out at the surface of the water. So methane, being nonpolar, does not dissolve in the polar substance like water. Whereas if we take table salt, you guys know that table salt does dissolve in water, and that what happens is that the polar water molecules, the partially negative oxygen is attracted to the partially positive charge on the positive charge on the sodium ion, and that creates a cage around the sodium ion, like so. And the chloride ion being negatively charged, the partially positive hydrogens are attracted to the negative charge on the chloride ion, and that will form, and again, these are partially positive. I'm not going to do all of them, but the partially positive hydrogens, again, attracted to the negative chloride. And that creates a cage around these two ions so that sodium chloride, the sodium ion cannot get back with the chloride ion, and we see it as dissolving. Now, if you add too much sodium chloride, yes, you reach the solubility limit. And solubility was talked about in the previous chapter too. It's actually referenced in the book, so there's something you need to look at, is what's the definition of solubility, and that comes back to the rules about solubility, which is, I think it's in chapter 4, rules of solubility, or the solubility rules, I should say. So that's something you need to look at as well. So that's what I think hurts students on chapter 13, is that it brings all to bear from from General College Chemistry 1. We expect you to know this, and now we're going to proceed with the new material. And you go, man, I don't remember molecular geometry or polarity, and I don't know electronegativity, or I don't know about solubility or the solubility rules that we talked about. You're going to have to get up to speed on that. And that's why I'm making this video, is to kind of get you prepped for this next week as to what we're going to be covering. So if there's something you need more help on this stuff that I've posted up here, just email me, and we'll try to find something to help you. But I think this is what hurts people in 13, is not knowing prior knowledge. Again, Lewis structures, molecular geometry, molecular polarity, bond, and then hydration solubility rules, and the whole thing here is that polar dissolves polar and nonpolar dissolves nonpolar, and so the overall theme here is like dissolves like. So let's talk about solutions. Solutions we had in chapter 1 in Chem 170. It's a solution is a homogeneous mixture. And so again, they don't talk about it here because it's understood that you know this, but that a solution is a homogeneous mixture. And homogeneous means all one phase. So you know what that is, like when you dissolve salt in water and it all looks like a clear glass of water. That's homogeneous. And a solution consists of two components, the solvent, which is present in the larger amount, and the solute, like the table salt that you add, which is present in the smaller amount. And we can take a certain volume of water and a beaker, and that's a pitiful beaker, but we'll go with it. So here's my water, and you know that you can add a teaspoon of salt, and it piles up here on the bottom. You stir it up, and it dissolves, and it's in the solution now. But eventually, you're going to add so much salt that it does pile up and it doesn't dissolve. So you've reached, at this point, you've reached at the point that you can't add one more salt crystal to the water and it not dissolve. That's called the solubility limit. So I want to stress this point is that an unsaturated solution, which is where you've added only enough solute for it not for all the solute dissolves, all of it dissolves. That's at a particular temperature. That's important. It's at a particular temperature. As long as it dissolves, you haven't reached the saturation point. The saturation point is when you've reached the solubility limit. So how do you know you've reached the solubility limit? Well, it's generally in tables. It'll say so many grams of sodium chloride will dissolve in 100 grams of water at a particular temperature. All right. Experimentally, how you do it is if you add a crystal of salt and it doesn't dissolve, even after stirring and so forth, you have exceeded the saturation point. And so once you add more solute than what can be held at a particular temperature and a particular volume of solvent, or mass of solvent, either way you want to think of it, actually mass, then you've reached the solubility limit. All right, so any more that you add, like this piece here, or if you pour in a full teaspoon, it doesn't dissolve. It stays. You see it as a lump of salt at the bottom of the beaker in this case. So really what's happening is some of the salt is dissolving, but some of the salt is going from ions in solution back to the solid. And that becomes an equilibrium. The rate of this dissolving, the rate of this returning as a precipitate becomes constant, and you've reached the limit there. Called solubility limit, and so that's your definition. Given volume of saturated solution is called the solubility. All right, how much can you dissolve of the solute in a given volume or mass is the solubility, and that has to be a specific temperature. And you guys know this. You know that if you increase the temperature for salt or sugar, you can dissolve more salt or sugar in a higher temperature than a lower temperature. Now, that's not the case for everything. There are some strange materials out there. As you increase the temperature, less dissolves. But for the most part, as you increase the temperature, you get more solute dissolving in the solvent. So saturated solution, make sure you understand it. Make sure you understand the definition. It's the maximum amount of solute that will dissolve in a given amount of solvent at a particular temperature. And then think about what it looks like visually. And really visually, you can't tell the difference between unsaturated and saturated until you add that one piece, one more little amount of salt. If it dissolves, it was unsaturated. If it doesn't dissolve, then you've passed the saturation point. You actually you're past the solubility limit. All right, next slide is, so you have to be able to define solubility and then define what type of solution you have. So it says, for example, the solubility of sodium chloride at 20 degrees Celsius is 36 grams per 100 milliliters. So this is mass per volume solubility. So what that means is I can add up to 36 grams of salt in 100 milliliters of water, and it will completely dissolve at 20 degrees Celsius. anymore, and it's not going to dissolve. And I've passed the solubility limit. I've passed the solubility. So anything up to 36 grams per 100 milliliters is called an unsaturated solution. It contains less than solute than has a capacity to dissolve. A supersaturated solution. Okay, let's talk about saturated before we talk about supersaturated. So here we are where, let's say I add 37 grams of salt to water. That means 1 gram of the salt is going to pile up here on the bottom. It's not going to dissolve. So I have 1 gram not dissolved. I have 36 grams that dissolved in 100 milliliters of water at 20 degrees Celsius. Here's the one that's tricky, is supersaturated. In a supersaturated solution, you have 100 grams of water, or 100 milliliters of water, but you actually dissolved more than 36 grams. So let's say I dissolved all 40 grams of salt in 100 milliliters of water. And it completely dissolves. Notice there's no pile up. It's all dissolved. That's called a supersaturated solution. You've dissolved more solute than what the solubility says should be dissolved. And you go, well, how would that ever happen? You may have seen this before. If you make rock candy, which is a sugar solution, you put a pot on the stove and you add about 4 cups of water, or maybe 1 cup of water, and then you add about 2 cups of sugar. So you've dissolved more sugar than can actually, and you heat this up, and so you can dissolve more sugar than normal, and then you let it cool slowly, and all of that sugar stays in solution. And then you can put some, string in here, or you can put some sticks in there, and over time the sugar will crystallize back onto the string or the stick, and we call it rock candy. So that's a supersaturated solution. So what's happening here is the crystals cannot form yet to precipitate out of the solution. But once they form, what will happen ultimately in a supersaturated solution is that at 20 degrees Celsius, we'll eventually get 36 grams of sugar dissolved. There'll be 4 grams dissolved in the bottom here, undissolved in the bottom in this 100 milliliters of water. So you actually see this all come out at one point. Another place you might see this, if you ever get one of those hot packs that you pop a little disc and all of a sudden it starts clouding up and the pack gets hot, that was a supersaturated solution, and as the crystals form, heat is released, and that gives you that warm pack. And then you can throw it in boiling water and recharge it. All you're doing is dissolving the solute back into the solvent, and it's ready to go again until you pop the disc again. So generally, the way we cause the supersaturated solution to precipitate its excess solute is we either scratch the surface of the inside of the beaker, or in the case of that little disc, pop it, and that little popping action creates a seed crystal, and once the seed crystal starts, all this starts precipitating out. Or you can actually add just a crystal of salt into a supersaturated solution, and that's a nucleation site, and that's what causes all of the salt to precipitate out until we reach the solubility limit. You guys have definitely seen this with the Mentos. So what you have there is you got a Coke, and all the carbon dioxide is dissolved into the solution, and then you add that Mentos, which has kind of got a rough surface, and that creates a nucleation site for the carbon dioxide to come out, and then all of a sudden the carbon dioxide comes out all of a sudden, and that ejects all the liquid out of the narrow opening of the Coke bottle. So that's a supersaturated solution of you've got a lot of carbon dioxide dissolved in a cold solution, and then once it's room temperature, as long as the cap's on, you're really careful about opening it up, all that CO2 doesn't come out, and then when you give it a nucleation site like the Mentos, all of a sudden all that CO2 comes out at one time, and you get this ejection of the liquid. So I want you to know the difference between unsaturated, saturated, and supersaturated solution. Again, unsaturated, you haven't met the solubility limit at a particular time. Saturated, you've met that limit. Anything extra is going to precipitate to the bottom, precipitate out. It may not go to the bottom, it depends on the mass, but it precipitates out. And supersaturated, you have dissolved more solid than you should at a particular temperature. And again, how do we know? If you scratch it or create a nucleation site or add a nucleation crystal, you ought to see the solution come out. And if you want to see a visual supersaturated solution, you can Google that and you can actually see multiple examples of that. All right, so here are different types of solutions. And most people think that a solution is a solid dissolved in a liquid, but here are multiple types. Here's a gas liquid. We talked about carbonated water. You can have a gas solid. We're going to talk about that when we start talking about catalysts, that you saturate a piece of solid with hydrogen and then you pass vegetable oil over that and you get Crisco. Liquid like ethanol and water. And then we have liquid solid, which is like if you have a mercury filling in your mouth, that's a mercury amalgam with silver, bonds together, and that's what creates your filling. You can have solid liquid like salt water, and then the last one is a solid solution like brass. So it's a metal solution, and they both cool, and we get a nice solid solution of copper and zinc, which we call brass. So you got to expand your horizons. It's more than just a solid dissolved in a liquid, but it is homogeneous. All right, so here, this intermolecular forces, this is where I see students really struggle when they don't have prior knowledge, naming, solubility rules, Lewis structures, geometry, polarities, and so forth. So if this is what's happening to you, you're going to have to go back and look at the material. So intermolecular forces is what holds molecules together. So what we're looking at here is you have a molecule, you have another molecule. What causes these to stick together? And they have to stick together if you want a condensed phase of a solid or a liquid. If there are no intermolecular forces, there's no attraction of one molecule to the other, you're going to have a gas, because each molecule is going to act independently of one another. So in order for things to become solids or liquids, there has to be an attraction between the two substances. Now what we're going to talk about in this section, though, is we're talking about solutions. So we want to know is when we put that solute in the solvent, what is that interaction? What is the interaction of the solute molecule surrounded by the solvent molecules? And we've actually seen that when I talked about sodium chloride dissolving. So let's look at that. We're going to see solute interactions. Let's draw a picture here again. So let's just draw a big picture here. Here's my beaker. Here's my water. So when I put sodium chloride in here, there is going to be interaction between one sodium chloride and another sodium chloride. And then we have solvent interactions. That's the interaction between a water molecule and another water molecule. And then we're going to have solute and solvent interactions. So there are three types of interactions that we have to quantify here to think about to determine whether sodium chloride is going to dissolve in water or not. And it comes down to these three interactions. All right, so again, here's a review of intermolecular forces, chapter 11 in this textbook, so you may want to read this, just the first two sections. If you read the first two sections and you understand this, you're in good shape. If you don't understand the first two sections of chapter 11, then I would say you probably don't understand molecular geometry and molecular polarity. You're going to have to go back to chapter 9. And if you can't do molecular geometries, then you're going to have to go back to chapter 8. And if you don't know the name of this or this or this, then you got to go into naming. Okay? So the thing that we're going to focus on is ion dipole. This is a dipole because overall this molecule has a dipole in this direction because this partially negative oxygen has a greater electronegativity than these hydrogens. So there's our overall force in this direction. And so because it's negative here around the oxygen, this positive sodium ion is going to be attracted to it. Then we have induced dipole, and what that does, this is called an instantaneous dipole, induced dipole, London dispersion force. So here we have a nonpolar substance. Carbon dioxide is nonpolar. It doesn't have a positive and negative end to it. There's no direction overall that the electrons are moving. But if we put it close to something that does have a dipole, it can cause the electrons to migrate away like so, and all of a sudden we have a slightly positive end here on this carbon dioxide and a slight negative end, and we have a negative end, partially negative charge on the oxygen, and that creates an attraction it's instantaneously, and that's how carbon dioxide can somewhat interact with water molecules. It's not 100% totally opposite repulsion there. So that's called an induced dipole. Induced dipoles happen in very cold liquids and solids usually, so that's where we will see this. And then we have ion induced, and that's even stronger. That's when you have a true charged ion in connection with something that's nonpolar. Two oxygens bonded together don't have a positive and negative region, but if you put a strong charged ion, positive ion, it is going to cause the electrons from the other oxygen to migrate this way, and now we have an induced dipole. So this is an ion-induced dipole. So these intermolecular forces are going to help us explain why substances dissolve in other substances. So this is what it looks like. We have a solute in blue. We have a solvent in white. Solvent's present in the larger amount. There's more white dots here than there are blue balls, or either way you want to say that. And so we start the process of trying to mix these together. And what we have to overcome is the solvent-solvent interactions. And we have to overcome the solute-solute interactions. And then there is going to be a solute-solvent interaction. So I guess we should have started here. So let me try this again. Here's what a pure solute looks like. Here's what a pure solvent looks like. We have to break the energy between the intermolecular forces, or reduce them between the solute atoms or molecules and the solvent atoms or molecules. And then once we break the solute, that's what's doing from here to here. And then we break the solvent, which is from the middle up to the top here. You see these are looser. There's more space between them. Then the combination of these mixing releases energy. And so if this release is greater than the overall input, then we're going to have a solution. So let's talk about this one more time. Here's the solute. Here's the solvent. They both have their solute-solute interactions, solvent-solvent interactions. It takes energy to lower the intermolecular forces, or to break the intermolecular forces between the solute molecules. That's what's happening here. And that's what this delta H is here. Delta H1 is greater than 0. It takes energy, heat, if you want to think of it that way, to get this to happen. Then to break the solvent-solvent interactions, it takes energy to do that. So these are endothermic processes. That was something what we talked about in Chem 170. Endothermic means energy has to be go with inside. It has to go inside this to lower the intermolecular forces. But then this mixing with this, and we get this, releases energy. And it almost always will release energy, because if it dissolves, it will, the mixing will release energy. It increases disorder, which is called entropy. This is much more disordered than this and this separate. It's more disordered than this and this separate. There's more disorder overall, which we call entropy here. So we're going to find entropy as a driving force for a chemical reaction, or for a mixing of solutions. Let's just say that this is a chemical reaction for a mixing of solutions. All right. So I hope you see that. This is a really important slide. It shows energy being input to reduce the intermolecular forces to separate the solute molecules. It shows energy being used to separate the solvent molecules, and then it shows energy being released, which is an exothermic process upon mixing of the solute with the solvent. So when we add this all together, this is called the enthalpy of the solution, the heat of the solution. And so we've added the separation of the solute, separation of the solvent, and the combination of the solute and solvent. These are endothermic. If it's less than 0, then it's an exothermic process. If the overall value here is a negative value, less than 0, then it's an exothermic process. Heat's given off. And this is what happens just like, for example, that hot pack. When you pop that disc, the solute molecules have to separate. The solvent molecules have to separate. There is a mixing there, and or actually let's say it this way, it's the opposite. It's the precipitation of the solute molecules releases energy, and we see that as an exothermic process. That's why I'll use it as a hand warmer. If you mix two things together and this comes out to be a positive value for this value here, if it's positive, greater than 0, then the solution is going to get colder because it's pulling energy. Let's say you have this in a beaker and you mix, I think, calcium chloride and water together as an endothermic process. You're going to feel the beaker get colder, and it's because the separation of the calcium chloride ions mixing with the solvent, water, is an endothermic process overall. So dissolution tends to be encouraged when it's exothermic, and it tends to be discouraged when it's endothermic. So that's why most of the time when you add two solutions together, if they mix together and they dissolve, it's going to generate heat most of the time, because exothermic reactions or processes encourage dissolution. Whereas when we mix things together and they don't dissolve very readily, or if they do, you feel the heat being pulled from your body to the container. That's an endothermic process, and those are much more rare than exothermic processes. All right. So here's what I've said before, and this is the main phrase that you get out of chapter 13. Like dissolves like. It's useful in predicting whether substances will dissolve or not. Okay? So it means that if the intermolecular forces are similar in type and magnitude, so is the intermolecular force the same, nonpolar, nonpolar, or polar, polar, and how large that force is, that will determine whether the reaction is mixing, and if it's great, it means it's probably not endothermic, it's going to be an exothermic process. All right, so let's look at an example of two nonpolar substances. So carbon tetrachloride, at this point you ought to be able to tell me the molecular geometry is tetrahedral. Oops, I did that wrong. Let's do it again. So it's tetrahedral, where there's a chlorine coming out of each corner of the tetrahedral. And benzene, you may or may not know this one. It is a cyclical structure. It looks like this. It's 6 carbons, and there's 6 hydrogens. We don't generally draw the hydrogens, but there's a hydrogen coming off each one of these carbons like so, and that gives it 4 bonds for each carbon. These are both nonpolar substances. And so, because they're both nonpolar, there's no direction. There's no dipole moment in one particular direction. The molecules are comparable in magnitude, so that's important. So they're both nonpolar, and their forces are intermolecular forces are comparable in magnitude. That means the two liquids will mix together and be soluble in one another, and that means the word is miscible. Make sure you know this term here, miscible. Got to speak the language. Miscible is the term, and if they don't dissolve, it's immiscible. All right, M. So you got to speak the language. Miscible means they are completely soluble in one another, and you would see that as one phase. It'd be a homogeneous mixture. All right, so let's look at these problems. This is a sample problem. If you can answer this problem without my help, you're in great shape. You understand section 13.1. You're ready to move on to section 13.2. So stop the video, write these down on paper, and see if you can figure these out. And if you can, then you're in good shape. If not, then you're going to have to decide, why is it you didn't get this correct? Is it from something from Chem 170, or is it something I didn't get out of section 13.1? So stop the tape, try them yourself, and then let's see where you are. All right, so let's look at these. So we're talking about benzene. We just said benzene is a nonpolar solution or substance. Nonpolar, all right. Doesn't have a positive and negative region in the molecule. And again, structure, we've seen it. Looks like a hexagon. It's aromatic. It's got hydrogens coming out like that if you want to draw those. But there's no it's no dipole moment. So what we have to determine, are these four substances here polar or nonpolar or ionic? So for bromine, if you did the Lewis structure for it, you would get two bromines bonded together, and each bromine would have 3 electron pairs around it. And because it's bonded with itself, you don't even have to actually do this. You know this is a nonpolar molecule. There's going to be equal sharing the electrons between the two bromine atoms because they have the same electronegativities. So bromine is a nonpolar molecule. Nonpolar. So if it's nonpolar and benzene's nonpolar, yes, bromine will dissolve in benzene. Sodium iodide, you should at this point in your sequence of classes know that sodium iodide is an ionic compound. It consists of sodium ions and iodide ions. And we know that ions dissolve in polar substances, but ions do not dissolve in nonpolar substances. So we would say no to this. There's no ion-dipole interaction because this doesn't have a ion polar substance. This is a nonpolar substance. So sodium iodide is not going to dissolve in benzene. Carbon tetrachloride, probably need to draw the structure, and this is where chapter 8 and 9 come into play, but the Lewis structure for this looks like this. Each one of these, I'm just going to draw it like this. This is my lone pairs to quickly get through it. Yes, the bonds are polar. Chlorine is more electronegative than carbon, but overall there's no molecular polarity. There's no molecular dipole moment. Like you can say the arrow of the dipole moment, the resultant force is in any particular direction. It doesn't happen here. And the reason why these are all partially negative, there's no way you can divide this molecule and get it strictly a negative region and strictly a positive region, which is what polarity is about. So, carbon tetrachloride is a nonpolar molecule, and so this will dissolve in nonpolar benzene. Formaldehyde, what does that look like? This is a tricky one. The Lewis structure looks like this. All right. Okay, looks like that. It's trigonal planar. It's AX3. This is an X, this is an X, and this is an X. So trigonal planar, it looks like a triangle. This side is slightly, this side is a polar. It is a polar molecule. This part down here is not so polar though. So we would say overall that because formaldehyde is polar, that it shouldn't dissolve in benzene. Okay? So let's check our answers. So here's how you do it. Notice you have to draw a structure. You have to draw a structure. Notice they show this on D, and hopefully they tell us the answer here. So let's go to one. So notice on the last one they couch it, and they say it's more soluble in water. And so if you said formaldehyde dissolves somewhat in benzene, I would give that as a correct answer, although they wanted to, the question was, does it dissolve in benzene? This one does dissolve in benzene. This one dissolves in benzene. This one dissolves in water, does not dissolve in benzene. But notice they say more soluble. It's not definitive. And they can't say that because a small amount will dissolve. But overall, that's what they were asking for. Formaldehyde will dissolve in polar water more so than benzene. All right. Actually, I misread that. Let's go back. I did. So they just asked which one does it dissolve better in. All right. So it is benzene. It is benzene. This one's definitely water. And because this one's polar, definitely water. Okay, they did couch it that way. All right. Sorry about that. So let's go back and make sure, because I just wasn't reading that close enough to doing my lecture here. But it did say, is it greater in water or is it greater in benzene? All right. So that makes more sense to me. That has a definitive answer. Things that are polar will dissolve in water. Things nonpolar, mostly nonpolar, will dissolve in benzene. All right, so I think that's about as much as we need to cover today. Like I said, I'll try to generate these videos if you think they're helpful throughout the semester, especially for Chem 180. If you have questions, just email me. If you need to actually discuss something, schedule a time with me through Teams by scheduling an appointment through bookings. And like I said, I know Chem 180 is difficult online. I'm here to help you, and hopefully this is helpful. So we'll